All right, welcome back, friends, to episode 28 of Uncertainty and Probability Theory, the Logic of Science. 2, 3, 4 episodes ago, classes ago, we talked about randomization, and there were some questions. Some people are particularly keen that randomization does something for you. I say it does not, except for one instance. And that one instance is to remove a known cause. To remove a known cause. So, as the example that we gave last time, if you want to have a kickoff in a football game or something like this, the referee flips a coin, and one side chooses head or tails or whatever it is, and whatever the coin is, that team gets to choose whether they receive the kickoff or not. That is a way of removing the known causes from the coin flip. We don't know and can't control those causes, or at least not very easily, or we assume referees don't try, but it is possible, but we assume they don't try. And therefore, there's no bias. There's no human bias in this. The referee, if he is for one side or the other, won't be able to manipulate those causes such that his favorite team gets the ball first or second or whatever it is that is assumed as an advantage. That kind of cheating, randomization is removing a known cause. Now we could use this in clinical trials too. For instance, we're testing the new drug Profitol against a placebo or something like this, and we don't want a pharmacological outfit, a pharmaceutical, in control of picking those patients who get the new drug and those patients who are going to get the placebo or some old drug or some old treatment or something like this, because the possibility of bias of them pushing people into the category of the new drug if they're not as sick, for instance. That's a cause. Their prior health is a cause, is a known cause that's going to be related to the outcome, whatever it is, getting better, for instance, with a pill. And so we don't want them to be able to get away with that, so we make them randomized. In other words, it's just like the coin flip, and again, we're removing known causes that are associated with the outcome, whatever it is. And we want to remove those causes. That kind of randomization is absolutely fine, and I never speak against it because, of course, we need to be able to make these tests as impersonal as we can. And the reason is, but not all scientists do this. You know, physicists don't do this when they're controlling an electron passing through an electron field or something like this. They're not randomizing the electrons or something when they're tweaking whatever the field properties are or something like this to see how much an electron deviates or something. They don't do that because it's presumed that they're not as interested as in the outcomes as pharmaceutical reps are in theirs. And so we don't require them to do these kind of randomizations. But they could just as easily do these kinds of things in physics experiments, although it sounds kind of absurd in that case, because in physics we want to know the causes, we want to know all the causes, and we want to control those causes. And that's exactly what we want to do in all other trials too. We want to control causes, or we want to understand what the causes are, what the conditions are. All the causes and all the conditions that led to some substance, something using its powers and causing the outcome, whatever the outcome's going to be. Other than that, randomization does nothing for you, except for removing some of those causes. And when we want to keep some of those causes, in statistics anyway, statistics modeling, we call it control. They call it control. That's a reasonable word when we're actively controlling things, as I'll demonstrate to you here in a second, but it's a very unreasonable word to use when you're just using a happenstance sample of data that you have and you're analyzing somewhere. Then you're saying, oh, I'm going to control for a sex. You're not controlling for anything. It's a terrible abuse of words to say you're controlling for something when you're just putting a bunch of crap into a regression or something. That's not control. as I'll talk about more when we do about models and everything. So let me go about this. I want to demonstrate to you, I didn't use any math before, but now I'm going to have to throw some math at you to show you that randomization, except for removing cause, except for controlling bias and cheating, does nothing for you. Does absolutely nothing for you. Let's try to think about this. Let's try to think, and we'll do it in the terms of, because people understand this, of a poll. We're trying to call people on the phone, get their opinions on something. Or we're going to give them a new drug, Profidol versus a placebo, or some old drug or some old treatment or something like this. Now, people come at us. Here's a person, call them subject 1. And they're going to have any number of attributes. Call this attribute 1, attribute 2, and we'll call this attribute P. We don't know what these are. These are going to be hidden attributes. Attributes we do not measure. All we know is we have a person, and we're going to give this person Profidol, and we're going to see if it cures them of splenetic fever or reduces their splenetic fever symptoms. That's all we know. These attributes, which this person possesses, are unmeasured by us and unknown. To us, anyway. The person might not even know that they have them, but these are all attributes that he has. We don't know the size of P. We don't know the state of these attributes. This is the point. They're unknown. But let's just run a thought experiment here and suppose you can have this attribute or not. We'll just, the simplest way to do this is to say each attribute, we could possess it or we don't possess it. That's it. So this person has, say, has the first attribute, doesn't have the second, and has the last. Okay, here's another person, subject 2. He also has these attributes, and it doesn't matter if he doesn't have attribute P. If he doesn't have attribute P, we just give him a 0. These are on or off. So we can have P in depth. There could be P plus 1, P plus 2, P plus 3, and they all are zeros, so it doesn't make any difference. Suppose he has the opposite. It doesn't make any difference. Now, we're going to talk next time in episode 29 about that nothing has a distribution. So I'm just going to ask you to believe for now, and a very simple thing to believe, is suppose in this population of people that we're going to grab for this sample, the population we're going to get, not a hypothetical population of infinite numbers of people in some weird situation, but the actual population we're going to get of people who are going to be signed up for our study in this. There's going to be a proportion of people, here's they don't have, and here they have for attribute 1. Suppose it's something like this. This is I'm drawing a little histogram here so that something like the way I drew it here, like, I don't know, like a quarter of the people don't have the attribute and 3/4 do have the attribute, whatever it turns out to be. And here's attribute 2. And I'll say that very few people have 1 and most people have nothing. And suppose, I don't know, doesn't make any difference. Suppose this is pretty much 50-50. Now, of course, in real life, they'll have not just attributes that are on and off, but they could be a measure. It could be a range. It could be a number, you know, between 1 and 100, or -15 and 42. Who knows? But for now, we're just going to make our life easier and look at this in terms of yes or no's. Just makes things a little bit simpler to explain, but it doesn't make any difference. And in fact, we'll see when we increase the complexity of this, it makes the situation worse for fans of randomization. Okay, now because we have this, we're going to go back to our statistical syllogism, which you remember we proved. If I have a person, just a random person, I see that's a word I got to be careful about using. If we just take a person, our premises are going to be, we're going to take a person from this pool of people who are going to be in our study. What is the probability that they have attribute 1? All right, so the probability, and I'm going to just label this proportion of 1s, I'm going to say is P1, P2, and that's an unfortunate terminology there, but PP, just proportion 1, proportion 2, proportion of the last one. I chose bad notation. Notation can kill you, as I've told you before, or it can help. So I'll just say, what's the probability the person has attribute 1? Turn on. Given this, I'll call it the distribution 1. Well, it's obviously going to be P1. We don't know what it is. We can't measure it. We don't know who has it and who doesn't, but we're supposed it'll be something. Whatever it is, it's going to be this proportion. We're going to suppose of all the things that they can have on or off, it'll be some proportion. And the same thing, probability of A2 given D2 will be P2, and so forth. Okay? This is true whether we know it or not. We don't know these P's, and it doesn't make any difference, as I'm going to show you, prove to you. And we don't know anything else other than that they might have these attributes on or off. Okay, you're with me so far, right? So, all right, so now we're going to have people, here's our same person. We're going to have some randomization scheme. They're going to go into group 1 or group 2. And how we're going to get that, we'll use the referee's coin. I'm sorry about the shadows of light on this thing. I'm stuck here at this particular scenario here, so I need to figure out how to handle this light. I haven't figured that out, but I didn't want to wait till I figured the light situation out before continuing on with the classes. I thought that would be not a good idea. So, all right, we're going to have some randomization scheme. R for randomization, like a coin flip, whatever it might be. So that a person has, in this particular randomization, we'll say a 50-50 chance of being stuck in one group or another. So when this person comes here, if he's in group 1, well then group 1 gets a person with attribute 1. And if this guy, number 2, also gets stuck in the group 1, then we have a person with attribute 1 and we have a person without attribute 1, and so forth. Okay. Now, we want to know, or at least I want to know, what's the probability of having attribute 1 given the distribution 1, which we don't know anything about, given they're in group 1, and given, I'll just call this our randomization scheme, R. That's not that they have been random, that's the information that goes in. This is information now about the randomization. It's going to be 50-50, like a coin flip, where we don't know or can't control the causes. And you do remember, I hope everybody remembers, I have created a coin flip machine which can give me heads every time or tails every time, so because I can control all of the causes. So we're saying here we're removing known causes with this R. That's all we're saying with this. So what is this? Well, we know that this is here. I claim that this probability of A1, given that they're in here, given they've been randomized to this group or group 2, and the randomization scheme is equal to this probability, which says, and it will be the same for every attribute. It will be the same for every attribute. If we do it for 2, we're going to get P2. This will equal P2. And it'll be P3 and P all the way up to PP. We can't get enough wee p's in statistics. If that's the case, the probability you get, it doesn't matter whether you just take these people. If I need to have M people in my drug group, my profit-all group, I can take the first M over 2 people, and I can assign the second M over 2 people to M into the second group. All right, I can just take them as they come. Take the first half of this group, stick them into the drug group. I could take the second half as they come in the door and give them the placebo. With a caveat, which I'll mention in a minute. You're probably thinking, oh, wait a minute, that might hold that thought in abeyance. It's going to turn out the answer is going to turn out to be control. All right. So let's look at this. It happens to be the case. So this is the probability I'm after. I want to solve this probability right here. What I can do is I can say the probability of A and G for any attribute, any group. It doesn't make any difference. It's the same math instead of just trying to keep all these subscripts in place here. this is just, we're just going to use Bayes' theorem here, is going to be probability of A given G dr times the probability of G given D and R. This is just Bayes' theorem. No problem with that, okay? And this is the quantity we want to know. So if you don't mind, well, I guess I could do one more line over here. I'm just going to rewrite this. Here's our probability that we wanted to know, G dr. And that's going to equal this creature, probability of A, G given dr, divided by, just divide this on both sides, probability of G dr. So far, so good. You're with me, right? The math is fine. So now I'm going to decompose this beast up here. I'm going to say the probability of, I could just do the same thing in reverse. I could do the same Bayes' theorem in reverse. Is this the way I did it in my notes? I hope so. Yes, it is. G given dr. There's so many notations flying around, I sometimes get mixed up. Probability of A given dr, all divided by the probability of G given dr. I can't forget that A right there. So all I did was just, I'm after this probability right here. I want to know this probability. This is the thing that we want to know. What's the probability of having the attribute given that they're in this particular group and they have this distribution, whatever it is, this, we'll call it a distribution for now. It's not the same thing as what statisticians say when they say distribution, or they do sometimes. The word is equivocated, and that leads to the fallacy of equivocation. Like I say in my book, you know, those make the worst fallacies but the best jokes. Like the one I like to tell, everybody's heard it before, you know, these two cannibals are eating a clown and one says to the other, "Does this taste funny to you?" That's an equivocation joke. We don't want to make an equivocation error here. So what I mean by distribution in this particular lecture is nothing more than this is it. This particular proportion of people have the attribute and this proportion do not. That's it. Okay, so I just used Bayes' theorem here, and that's exactly what this equals. And then this is the probability we want to know again, and that equals this divided by this. And then I could use, I could just bust this out. Probability of AG equals the probability of A and times the probability of G given A. And then we'll look at this. What's the probability of A given dr? Well, the randomization scheme does nothing. Just knowledge of how we're going to randomize anything doesn't change whether a person has the attribute or not. So this particular probability, let's see here. This I'm going to have to, because I'm lacking board space here and I don't want to erase anything. This probability here, the probability of A given dr, I say to you is the same as the probability of A given D, because knowledge of how a person is going to be randomized, not that they have been randomized, but knowledge of how they could be randomized, that's all R stands for, is the same as the probability of A given D. We haven't randomized them. We're just saying if I'm going to use this randomization scheme, it means nothing to whether or not the person has this attribute. So that probability is AD. Now, given the probability that they have this attribute, so given the probability that they're in this group is entirely by this coin flip right here, and is not related to the attribute. That's the whole point of this. We're going to flip the coin, and they're going to be set into one group or another. That's the randomization scheme. So this probability, the probability of G given A times D, given A dr, is the same as the probability of G given dr. And so we have G dr, we have G dr here, and we have the probability of A given D. And that's exactly what I claimed it would be. So randomization has done nothing. The probability a person has this attribute, given that they've been assigned to group 1, is, and it doesn't matter what kind of randomization scheme we have here. I could have put, and sometimes I just read a paper, this fecal transplant, they do fecal transplants to people who suffer from certain diseases, people who have more healthy biomes in their colons and so forth. And the hope is some of that activity, if you do a fecal transplant from a healthy person into an unhealthy person, some of that biome will help grow in their gut. and provide benefits. This was in Parkinson's disease, I guess it was. And so in the drug trial, they had, I think it was, they randomized 2/3 to 1/3. Doesn't make any difference. This doesn't make any difference because this is just the randomization scheme. It says nothing about what particular randomization we're doing. It does not have to be 50-50. It can be anything we want, 90-10, whatever, 99-1. It really doesn't make any difference. The whole point of this, though, is to show you it doesn't make any difference. The probability in the end that they have the attribute, given that they're in this group, is the same as the probability if they have the attribute if they're in this group. It's exactly the same, which is the same as the probability if they have the attribute altogether, which means randomization does nothing. Now, I wrote some code for this because some people they're not convinced by the actual proof, but they would be convinced by doing some simulations. We're going to talk about simulations in depth later and why they don't do what is claimed they do at another time. So I won't belabor that right now. But I wrote the code so you can play with it. I'll put it on the website. The link's going to be down there if you're just watching the video at one of these sites, or it's going to be at my site. If you're on Twitter looking at this, the tweet under this will have the link to my site or the Substack, and I'll have the code there. You can just play with it. But basically what it does is simulates a bunch of people who have these various attributes, and then we take them half and half, like I told you, or we randomize them, and in the end, the proportions are the same. All right. I'm going to have the written lecture on all this too. So if this is confusing, I went too fast or something like this, it will be in the written lecture as well. So now let's move to another topic. We're running out of time already. This is the problem. I just can't. Randomization of words coming out of my mouth, I think. All right. Let me try to explain. The idea should be simple anyway. We have a person coming to us, and they have a whole bunch of attributes that we don't know anything about. And here's another person who has a whole bunch of attributes we don't know anything about. If we don't know anything about them, mixing them up is not going to give us any information about what they have. And so it's not going to help us in our groups. But there might be, you're thinking to yourself, oh, wait a minute here, I got an idea, maybe it does help. So I don't like your idea of splitting them. So here's all the attributes they have, and here's time. And here's time that we entered people into the study. And here's the last person, time, and they all have all these attributes that they don't make it have. And by the way, I didn't show you the math. What if they have levels to all these attributes? It just gets worse for the case of randomization, as I hope you can see, because if we don't know what the value is, randomization doesn't tell you what the value is. The probability of the person being in the group, the randomization group, having whatever attribute you have or having whatever value for attribute that if it's a value and not yes or no, doesn't change. It just doesn't change. You can't get information by taking information away, which is what randomization does. But you might think, oh, Briggs, you said you're going to have all this by just taking the first half who walk in the door and then take the second half, and this is time. But I don't know. So suppose I get all these people in the morning, and I get all these people at the end. The first half of the study are all morning people, and the second half of the study are all evening people. And that very well could be causally related to the outcome. So shouldn't I just randomize these? Yes, you can. But what are you doing? You're not randomizing them. You're controlling for time, because you know that time might be causally related to the outcome, because people who come in the morning, maybe they're older, men, for instance, who have different health problems, and I'm just throwing out a supposition here, I don't know, maybe it's women who come in the afternoon and they have, maybe they're just as sick but in a different way, or maybe they're healthier, or who knows. And that could all be causally related to the outcome. So in this case, you would control for time. You say, I can't do this, so maybe in this case I can take every other. So I make sure to get an equal number of AM and PM people in my sample. We do this already for if the next one is sex. People often control for sex. We're not going to leave this to some fluke of randomization because, and the next thing I'm going to talk about, oh gosh, I'm already out of time. The next thing I'll talk about is, just by flipping coins and everything, it could be I get most of the males in one group and most of the females in another group, and that just wouldn't do, because we know up until until the great wokeology happened, that sex is related to all sorts of health outcomes. So we would control for sex. We would make sure that we had as many people and many males in the drug group as we had females in the control group, or whatever proportion that made sense to the outcome causally. We're always trying to think about cause. We would control for time. We would control for sex. In the real sense that we're putting these people in these groups because we know these are a potential cause. We haven't even talked about the word correlation. People throw about the word correlation. Well, Briggs, what about those attributes? What if they're correlated? Well, what do you mean by that? You mean they're causally related in some way. The math doesn't change. The math gets a little more complicated. The outcome doesn't change. Just because we still can't get from ignorance to knowledge by adding more ignorance. We start with ignorance of all their attributes. We add ignorance by removing cause with the randomization. We can't get to knowledge at the end of this. It's just not possible. And in fact, in the waning minutes here, here's the number of attributes that a person has. Everybody's going to have at least one. So 1, and we'll just have this go off to a very large number. And here is the probability of, we'll call it at least 1, in really crappy location. So suppose in the sample that I have, in the population, eventually I'm going to have 2 groups. I'm going to have a drug group and I'm going to have a control group of some kind. And I want to know, if I'm comparing against all the hidden attributes, what happened? How many people how different are these groups in terms of their hidden attributes? Or whether I'm going to just take them as they come, or I'm going to randomize. And the idea is very simple. The more attributes that they have that are important causally, or just the more attributes that they have, whether or not they're causally related, the bigger the chance, this should just be sort of obvious, the bigger the chance that I'm going to end up with one group with a lot more of people who have that attribute than in the, if they only have like 1 or 2 attributes. So for instance, if I just have sex and there's nothing else, sex is the only thing that makes any difference whatsoever, and they have no other attributes besides sex, I'm gonna flip the coin and split the people up. If I have a very large sample, I'm gonna get roughly 50-50 males and roughly 50% males in one group, roughly, and 50% females in the other group, roughly. Fine. But I'm also going to get, and if they have attributes, I'm also going to get the proportion of attribute 1 is going to be in the group, the first group, and I'll have a different proportion of attribute 1 in the second group. Just because people come in mixing up, not everybody is going to be the same. It could very well be that people have come to you first and they all happen to have that first hidden attribute which you knew nothing about, or the second attribute is like that, or the third, or the fourth. And if you have a very large number of attributes, the probability, here's 0. I'm probably explaining this badly. I'm going to write it better, I think. The probability that there's going to be differences, of important differences between the groups, the probability that there's going to be important differences between the groups in terms of numbers of attributes, or the differences in the groups. Here's group 1, and here's group 2, and there's going to be, here's the proportion of attribute I. And in this group, here's the proportion of attribute I. And a lot more of them happen to be, for whatever reason, happen to be in this group. The probability that we get discrepancies like this, it depends on the size of the discrepancy and so forth. What we really want, ideally, is everybody would be If everybody was, they would be split by their proportions, by those proportions we had before. There would be the same proportion here for I, and it would be the same proportion here for I. But we might not get so lucky. And so maybe it's not attribute I, it's attribute J that's different. The probability we get at least one of these imbalances goes to 1, very obviously as the number of hidden attributes increases. And it goes even faster if we're looking at measures and not yes or no attributes and so forth. This should be sort of obvious to you. In the same way that you know, you throw a bunch of beans on the floor and you can connect the dots and make any kind of picture you want. It just is going to happen. So again, randomization can't stop this. Randomization is not going to give you this. We already saw it couldn't do anything for you anyway, and it's not going to prevent something like this as the number of attributes go up. So, and in the end, it's going to turn out, none of this is going to turn out to matter anyway, because what's important are the attributes, the conditions that are causally related to the outcome. That's what we're always after in this, and what we always really want. If we could control that, that's why, like in those calometric experiments and so forth, where we're trying to measure the increase or decrease in heat by making some change, like cold fusion people did and so forth. We have to be very extremely careful to control for every possible source of extra heat. And if we don't, we're missing control. And so you can make that mistake and not know. That's one thing. And that's why these experiments are often incorrect, because people don't know. But randomization is not going to fix it for you. All right, I went on a little overtime here. All I can hope, you can look at the code, you can play with the code, but please do read this. And next time we're going to talk about nothing has a distribution. So those pictures up there, I'm going to convince you those don't matter. Nothing has a distribution. All right, that's it for now. Thank you very much for listening. More information is below.